All right. Good morning, everyone. So, I hope you guys had a good time during the reading break. So, sana nakapagpahinga kayo and was able to catch up with sleep or rest, or kung di naman you were able to catch up with some of your academic lags, probably incurred during the first half of the semester. Kasi siguro medyo heavy ang semestre na 'to para sa inyo, especially for I know for a fact sa mga BS Math, mabigat yung, 3rd year, first semester kasi sabay-sabay yan, Math, 155, Math 111, and then if you took, Math 174 as an elective, so that's a pretty heavy, workload for the semester. How about yung mga applied math? May mga applied math ba dito? Gano'n din ba kabigat ang 3rd year, first sem sa inyo?
Ako po, sir, applied math po ako and medyo nabibigatan din po ako.
Okay, I see. Puro majors, no? Kasi ito yung start ng major year nyo. And you don't have any choice because during the first sem of your fourth year, dapat nag-start na kayo sa research, either your SP or your thesis. So kaya siksikan yung third year, first and second semesters. But good thing we have a reading break, so hope you guys were able to catch up with the lessons, not only in our course but also with the others. Now, I hope you also had the time to look at the problem set results. I was able to finish it during the reading break. So, and then I'm looking now at the standing of the class, and it's pretty good. The average standing for the class is about 87%. So good job, guys. Please keep it up, or not, or if not. Do better for the next semester, for the next half of the semester, but it's a pretty good place to be during the middle of the semester. Now, medyo kulang pa yata ng konti. There are two lab sections na hindi pa tapos yung lab excerpt 3, or hindi pa tapos mag-grade yung lab excerpt 3. So kindly wait for it. What else? Oh, I read the comments that you guys wrote in PS 1.1. And some of you are still having troubles with the programming part of the course. Unfortunately, yun nga yung sabi ko, the Math 174 is not really into programming, pero malaking component niya dapat yung marunong na kayo mag-program. Either it was assumed that you already know how to write quick programs sa math, or from AMath 152, or at least na meron kayong idea paano magsulat ng simple codes from other courses. Pero I see that some of you are still struggling with it, and actually I don't want that to be the main hindrance or the main difficulty for the course. So kasi mas gusto ko mag-focus kayo sa concepts rather than the programming aspect of the class. That's why in each of the modules I ask your lab instructors to come up with a sample code, a pseudocode, or an algorithm to guide you with writing the program on your own. Pero yung isang ang problema, iba-iba kami ng programming language, and I cannot prescribe one single programming language for everyone kasi nga hindi ito isang programming course. So the idea is that you can uh, you can use any software or any program that you'd like kasi nga dapat hindi naman ito isang programming course. But since some of you are still struggling with the programming part, I am thinking of putting up a programming clinic, in particular a MATLAB clinic. So, in-announce ko na rin to dun sa kabilang klase. I just want to see if some of you guys will be interested to join. So, sabi ko sa kabilang section, kung may 5 o higit pa na gustong umattend nung programming session, specifically MATLAB programming, then I will be more than happy to put up a clinic about the basics of MATLAB, not only for the benefit of this course, but also for your SP or your thesis. Baka magamit nyo sa mga susunod na panahon yung programming skills na makukuha nyo with MATLAB. I'm specifically inclined to do MATLAB kasi number one, dun ako sanay. Number two, I think siya yung isa sa mga pinakasimple. Maraming mga toolboxes na available, so we don't have to write um, programs from scratch, especially if you will be just applying existing methods. Halimbawa, kung nag-ESP kayo sa applied math, tapos optimization yung problem nyo, hindi nyo kailangang isulat sa yung genetic algorithm or hindi nyo kailangang isulat on your own yung optimization on a bounded interval or unconstrained minimization kasi meron ng mga toolboxes si MATLAB na one-liner lang yung pagtawag dun sa mga methods na to, lalo na kung standard methods yung gagamitin nyo. And then number three, I want to take advantage of what the university offers. MATLAB license is not cheap, so it's a privilege for us at UP subscribe to MATLAB. So why not take advantage of it? So I hope somebody will volunteer in the class to get the names of those who would be interested. And if I will get the names or a commitment that at least 5 members from this class or any other class, mga taga math division, even your classmate, even your friends who are not yet taking 174, um, would like to attend, will have the commitment to attend such a clinic, then that will be great. So I can prepare and schedule something for the next couple of weeks. Okay. All right. Now, what else? Do we have other housekeeping matters? I think that's it. Unless you have questions so far. Kung may mga tanong kayo dun sa grading ng problem sets, ako yung sisisihin doon kasi ako yung nag-grade ng lahat. So, just send me an email or a chat kung may tanong kayo or gusto nyo i-clarify bakit ganito lang yung points na binigay ko to a particular problem of yours or solution of yours. And then let's discuss it. Okay, and with that out of the way, let's go to module number 7. Now, module number 7 is in part a continuation of module 6, which is about numerical differentiation formulas. So remember from last time or 2 weeks back, we talked about some ways on how to develop numerical differentiation formulas. In particular, meron tayong dalawang methods na nakita. Unang method ay kapag meron kang discrete set of points, tapos gusto mong i-approximate yung derivative at a number between the smallest and the largest abscissa. So ang pwede mong gawin is to generate the interpolating function, say an interpolating polynomial, that will pass all these points, and then pag nakuha mo na yung interpolating polynomial, siya yung i-differentiate mo. Tapos may inherit nung derivative na yon yung domain ng interpolating polynomial. So say ang interpolatory interval mo ay AB, meron kang n plus 1 points between A and B, then makukuha mo yung degree n interpolating polynomial whose domain is restricted to the closed interval AB. And you can use that to approximate the derivative at any number between A and B. Yun nga lang, yung derivative natin ay magiging degree n minus 1. On the plus side, that's fine because what we get is a polynomial back. Madaling ipa-implement sa computers. Pero ang drawback niya is kapag ka malaki si n. We know that when n becomes very large and we are using equally spaced points, or in some cases when we are using an arbitrary set of abscissas, then this interpolation process might be subject to the Runge phenomenon where the L infinity error blows up. So, ibig sabihin, kailangan pag malaking degree, medyo extra careful tayo kasi yung malaking error na nakukuha dahil sa Runge phenomenon ay pwedeng ma-inherit ng derivative. And this is unavoidable, especially if we have fixed abscissas. So kasi ang paraan lang para ma-avoid yung Runge phenomenon ay either gumamit ng special nodes like the Chebyshev nodes na nakakapagpababa ng L infinity norm ng error. So napapababa niya yung mga oscillations. Or number 2, gumamit ng piecewise interpolants katulad ng splines na pwede niyong i-differentiate. Now, aside from that, we introduce another method which involves finite differences. Dun sa finite differences na yun, we took advantage of a classic result from analysis, which is Taylor's theorem. So, pwede natin gamitin yung mga kapitbahay ni X, yung mga information around the neighborhood of X para i-approximate yung f prime of X. and we were able to develop a methodology on how to derive a numerical differentiation formula using specified points around x with certain order of convergence. And in this module, we will try to develop further improve these numerical differentiation formulas. So if you have a copy of Module 7, you will see in the Before You Proceed section, we have adjusted we have adjusted the timeline here. So the synchronous lab session for Modules 6 and 7 would be on Monday, November 15th. Luckily, na-schedule siya outside of the coverage of the recent memo from the Office of the Chancellor na pinagbabawal sa mga faculty members na magpa-submit ng requirements for this week. So yeah, so this will push through. So Lab Exer 4 will cover topics from modules 6 and 7, and the actual lab exercise is contained at the end of module 7. So the deadline would be right before midnight on Monday. So take advantage of the lab sessions on Monday. So kung merong mga hindi klaro or kung wala talaga kayong time na gumawa during the week, so you can do it during the lab session on Monday. You have 3 hours to do it, and I requested your lab instructors to write this lab exercise so that it would be good for 3 hours. Okay. So in particular, our objectives for this module is number one, find optimal step size for a machine implementation of a numerical differentiation formula. And that would be the entirety of today's discussion. And then on Thursday, we'll try to devise a way to accelerate the convergence of a numerical differentiation formula. And thirdly, we want to use this improved numerical differentiation schemes to solve scientific problems. Yan yung gagawin nyo sa lab exercise number 4. Okay. Now, here we go. Let's start the formal discussions, and let's start by recalling the 3-point centered formula of order 2 that I think we derived it last time. So ito yung formula or approximation para kay f prime using 3 points. So essentially, since we are approximating f prime of x, ang gagamitin natin ng mga data points ay nagsisimula kay f of x. All right? So, or x comma f of x. And then we are using 3-point centered formula. So, kailangan natin ng dalawa pang points. Kaya lang centered formulas. So, dapat nasa gitna si f of x. So, we move one step forward and one step backward using a uniform increment h, right? So, equally spaced yung mga data points na ginagamit natin o yung mga abscissas na ginagamit natin. Okay. And then if you remember, we derived this by looking at the Taylor expansion of f of x minus h and f of x plus h, and then solve for f prime, forcing the issue na yung mga unwanted derivatives ay magka-cancel out. And the only restriction here is that the formula should be of order 2. Ibig sabihin yung error term dapat ay factor in h squared or a multiple of h squared. And true enough, we have seen that the error or the theoretical error involved in this approximation is actually minus h squared over 6 f triple prime of c, where c is a number between x minus h and x plus h. All right? So ito yung na-derive natin from last time. And let's further investigate how this works by looking at an approximation for f prime of 0 where f of x is equal to e raised to x. Okay? Medyo simple yung example, pero it would be a nice simple example to illustrate the anomaly that I want to address today. So kung si f of x ay e to the x, so ibig sabihin si f prime of x ay e to the x lamang, so f prime of 0 is equal to 1. And though silly it might look, pero gamitin natin itong 3-point centered formula para i-approximate si f prime of 0 using different step sizes. And let's see what will happen. Okay. Now in table 7.1, I have tabulated the absolute errors incurred at specific or at certain values of h. So kapag ang ginamit nating step size h ay 10 to the negative 1, yung absolute error, which is computed as the approximate minus the actual value, and then we take the absolute value, ang makukuha ko is around 1.67 times 10 to the minus 3. So it is not that big. So probably in some applications, you'll be happy with this absolute error. Oh, by the way, typically, ang ipe-present ko sana ay relative error. Tama? Kasi mas madali yung i-interpret kasi percent error yon. Pero dito sa example natin, yung actual value na ina-approximate natin ay 1. So pag kinuha ko yung pag kinuha ko yung relative error, it's just that the absolute error divided by 1. So dito, equal yung absolute saka yung relative error. So kaya tinawag ko na lang siyang error. So here you see that, yeah, that's 1.67 times 10 to the minus 3. And then if I decrease the step size by a factor of 10, so from 10 to the minus 1, I'll put it down to 10 minus 2, makikita niyo yung error ay bumaba to 1.67 times 10 to the negative 5. And this is somewhat expected kasi ano nga yung order nung formula natin? Our formula is of order h squared, right? It's a big O of h squared because the error bound is the theoretical error is asymptotically bounded above by h squared. So f triple prime of c would be a constant, right? So kasi si f triple prime is assumed to be continuous, so it would be bounded on the interval x minus h to x plus h all over 6. That's also a constant. So basically, the theoretical error is a factor of h squared. So the idea is, since si h ay dinivide natin by 10, tapos yung formula natin ay order h squared, so ibig sabihin yung error dapat ay mabawasan by 2 orders. And you will see that is manifested in the table because now the error is down to 1.67 times 10 to the negative 5. Again, the interpretation of the order of the formula is that um, the error goes to 0 as fast as how h squared approaches 0. So magkasing bilis nag-approach kay 0 yung h squared at saka yung error. So kapag kasi h, dinivide nyo by 10, sa isang formula of order h squared, yung error madidivide ng 10 squared. Okay? So kaya from 10 to the minus 3, expected din natin na bababa siya sa 10 to the negative 5. And then if from 10 to the negative 2, I further decrease the step size by a factor of 10, bringing it down to 10 to the negative 3, right? Then yung error, expected ko, mababawasan siya ng factor 10 to the negative 2 also. So, and true enough, we got 1.67 times 10 to the minus 7, doing it another iteration, nabawasan uli ng 2 orders yung magnitude ng error, and so on. But there is some sort of an anomaly here when the when the step size goes down to 10 to the negative 7. Kasi ang error na ngayon ay 5.26 times 10 to the negative 10. You can think of this as a massive underperformance of the method itself. Kasi kung nasunod yung order of convergence, ano dapat yung order nitong error na to? Anyone? Ano yung ini-expect ko dapat na order ng error sa step size na 10 to the negative 7? Okay, anyone who has a guess? 10 to the what yung ini-expect ko na error kapag ka 10 to the negative 7 yung step size based on this table? May gusto bang humula? Sayang yung recitation points. Maliliit na bonuses, pero pag naipon yan, malaki-laki rin yan. So, anybody who wants to try? Ano yung ina-expect kong magnitude ng error? Oh, yes. Go ahead, Christine.
Kasi po sir, yung 10 raised to negative 6 dapat po, 'di ba, na-raise po siya to negative 13. So hula ko po for 10 raised to negative 7, dapat naka-raise po siya to negative 15.
Uh-huh. Medyo advanced yata yung sa'yo, Christine, but I think you had the right idea. Okay, thank you, Christine. Yeah, that's the idea is correct. Though yung 10 to the minus 6 yung error ay 10 to the negative 11. So, pag nagbawas ka ng factor na 10 dun sa error, dapat yung order nung error, dun sa step size, yung order nung error dapat ay mababawasan by 2, right? So, from 10 to the negative 11, dapat yung error dito ay 10 to the negative 13, right? And then that pattern should hold on and dapat pababa ng pababa yung error in a fast pace. Dapat kasing bilis ni h squared nga yung pagsa-zero ng error. But you look at this, when the step size is 10 to the minus 16, we have 44.5% error, which is very big. And this is counterintuitive, or this is counter to our idea of the theoretical error. If we go back to the theoretical error, ito dapat yung error, right? Pag kinuha ko yung limit nitong error na to as h approaches 0, we will get 0, right? Kasi yung f triple prime over 6 ay constant lamang, and then h squared goes to 0, so the entire expression should go to 0. But in our machine implementation, that's not the case. When we further decrease the step size, mukhang nagkakaroon ng pangit na behavior yung error. Ano kaya yung dahilan nito? Have we found an example that will break and the entire numerical analysis discipline? Counterexample pa to, o ano kaya yung posibleng nangyari? Ano yung anomaly or bakit merong underperformance yung method natin, even though we said na dapat yung error ay bumababa sa zero kasing bilis ni h squared. Pero it seems that that is not the case. So ano kaya yung nangyari? Anyone would like to venture a guess? Ano kaya yung posibleng dahilan? Bakit ganito yung nangyari? Mukhang may something fishy with this particular example. Bakit hindi nagze-zero yung error? Okay, 3, 2, 1. Walang gustong humula. Okay, the thing here is that this behavior of the error is from the theoretical point of view, meaning dun sa pagkakadesign ng algorithm, ganito yung ine-expect natin. But once we go out of the paper and transfer to a computer, things might get messy. Kasi ang idea, because the thing is, our computers or computing devices are finite in nature. So ibig sabihin, at some point, kapag ka nagko-compute tayo, especially with irrational numbers, or actually even rational numbers with a non-terminating number of decimal digits, so kailangan niyang i-truncate ni computer up to some point depending on its capability, right? Or ng computing software nyo, kung ano man yung settings niya. So halimbawa, meron kang ang exact number with say 25 decimal or significant digits, but your computing device only allows for 16 significant digits. So what your computing device will be to neglect the 17th up to the 25th decimal digit or significant digit and just use the first 16 to carry out the calculations. Tapos pag tinruncate niya yon, maki-carry over yung error, magpapatong-patong yan, magiging propagated error na siya. Kasi every after operation, ang nangyayari ay nagre-round off na siya. So, ang idea, ang reason dito, bakit nagkaroon ng ganitong behavior, kasi inimplement natin siya sa isang computing device, which is finite in nature, so we are not getting the exact values for the data. Okay, natratruncate siya up to some decimal digits. Okay. Um, so because what happens in the machine is, di ba ang kailangan nating data ay yung mga f of x plus kh, where k is an integer. So in our case, k takes the value of 1 and negative 1. Pero instead na instead na yung data, yung exact value ni f of x plus kh, yung nakukuha natin. Ang ginagawa ni machine, tinatruncate niya to. So instead of this actual exact data, ang ginagamit niya ay si y sub k. Alright? Where y sub k conforms to the numeration system present in the machine. So kung yung computing software natin 16 significant digits lang, so kahit ilan pa yung significant digits ng actual value, it truncate niya to, puputulin niya yung number of decimal digits, gagamitin niya lang si y sub k. So in the formula calls for f of x plus kh. However, the computer can only accommodate y sub k. So essentially, instead of implementing the numerical differentiation scheme that we have derived, ang ginagawa ni computer, ito yung kinocompute niya. Okay? In the case of our example earlier, ang kinocompute niya lang, truncated value minus truncated value all over 2h. So by the way, the notations here are, so yung truncated value ni f of x plus kh ay si y sub k, alright? So, and then k can be a negative integer. So, ibig sabihin si f of x plus h, ang ginagamit ni computer instead of the exact value is y sub 1. And then f of x minus h, ang ginagamit ni computer ay y sub negative 1. Okay? So ito yung cases when k is 1 and negative 1. So yung formula natin kanina na f prime of x is approximately f of x plus h minus f of x minus h all over 2h, hindi to na-implement perfectly ng computers. Ang ginagawa nila, pinapalitan nila yung data kasi baka sobra yung kanilang decimal digits by the truncated versions y1 and y sub negative 1. And this is not what we derived theoretically. So ibig sabihin, mababago na ngayon yung error term. Yung error term hindi na lang due to the theoretical error, which is the error due to the derivation of the method itself, pero kailangan nating i-factor in yung truncation error. So what we'll do to analyze this is to take into account for the truncated versions. So gusto ko silang masulat as equality. And I will denote yung mga naputol na decimal digits to be e sub k. Right? So para yung y sub k plus e sub k ay maging equal eksakto dun sa data point. Para lang to dun sa analysis natin nung bagong error. Alright? So, ibig sabihin, si f of x plus h, pwede kong isulat as y1 plus e1. Tapos si f of x minus h ay equal dun sa computer version, y sub negative 1, plus yung round-off error o yung truncation error na e sub negative 1. Right? So, is that good so far? So, I hope the notation makes sense. And then tingnan natin ngayon, ano yung total error? So, yung pinakita natin kanina, siya lang yung theoretical error, yung negative h squared over 6f triple prime of c. Siya lang yung dahil dun sa approximation na ginawa natin using analysis techniques. Pero ngayon, kailangan nating i-factor in yung error also coming from the computer. So, what we'll do is, ito yung na-derive natin na na formula para kay f prime. Ito yung ini-implement ni computer. But to find the total error, kukunin ko yung difference between f prime, which is the exact value, minus the computer approximate, f prime tilde of x. So ito yung approximate na nanggaling kay computer. So sabi nga natin, ang in-implement ni computer ay truncated version minus truncated version all over 2h. Siya si f prime tilde. Okay? So we subtract these two from each other to get the total error. Okay? However, I want to involve the theoretical error here. So I will expand this a little bit para maging kamukha siya nung nandun sa actual numerical differentiation formula. I will write it this way. Okay? Kasi ito yung actual derived formula natin para kay f prime. Okay? Why? Kasi ito yung computer version plus the truncation error. Binalik ko lang siya. Alright? So basically, this sum here is f of x plus h. Right? Kaya lang gusto kong ma-maintain yung equality nito at saka nitong nasa second line. So kaya yung dinagdag ko rito na E1 all over 2H ay babawasin ko ulit. Okay? Para makancel yung dinagdag ko, babalik ako sa Y1 all over 2H. Tapos ganun din yung gagawin ko sa Y sub negative 1. Instead of Y sub negative 1, I know that the ideal scenario is that I will use Y sub negative 1, the computer version, plus the truncation error. Kaya lang again, to preserve the equality between these two lines, I want to get rid of the minus e sub negative 1 over 2h that I added. So kaya nandito siya. Naka-minus siya sa dulo. Okay. So I hope that's clear. It's clear that this is equal to this guy. The reason I want to work with this particular form is that I can group the first two terms. Okay? Pwede ko silang pagsamahin into a group, tapos nakahiwala yung truncation error. Because this is essentially f prime minus f of x plus h minus f of x minus h all over 2h. Tapos eto na yung na-derive natin from last time. So we know that this is equal to negative h squared f triple prime of c all over 6. Ito kasi yung theoretical error. Plus the truncation error, the error due to the machine implementation. So yung total error dun sa 3-point centered formula na pina-implement natin sa computer ay equal dito sa sum na ito. Right? Where still C is a number between x minus h and x plus h. Okay? And then tingnan natin, ano yung mangyayari when h approaches 0? When h approaches 0, anong mangyayari dun sa total error? So yung total error ay magiging malaking number. It will approach positive infinity. Why? Because the first term vanishes to 0. Nakita na natin to kanina. And then here, E1 minus E sub negative 1, this would be bounded by a constant depending on the machine epsilon. So you can think of this as simply a constant. Kaya lang yung h nandun sa denominator. So this is bounded by a constant divided by a very small number. So the second term will blow up to positive infinity, right? Actually, medyo I need to be careful about it. Lagyan ko to ng absolute value para sure ako na pupunta siya sa positive infinity. Because it might happen that it will go to negative infinity. But the point is here we see that the error will blow up when h approaches 0. So, isang malaking consideration ito para sa atin kapag ka nag-i-implement ng isang numerical differentiation formula sa computers. We want h to be small enough to drive the theoretical error smaller. Kaya lang, we don't want the step size to be very small so as to incur a blow up of the round-off error. So medyo may balancing act tayo dito na dapat gawin. Kailangan balancein natin si H dapat ay sufficiently small para lumiit yung theoretical error pero hindi ganun kaliit na magko-cause ng paglaki ng round-off error. Okay? And perhaps okay. Now, the thing here is how do we optimize or how do we get that balanced H? Yung H na hindi ganun kalaki at hindi rin naman ganun kaliit. So let's look at a way on how to approximate the optimal step size. Okay. So going back to our scenario earlier, so ito yung total error na derive natin kanina. Okay. Tapos, okay. I'll just take the absolute value of it, okay? And then this guy will be bounded above by something. So yung f triple prime, pwede ko siyang palitan ng constant. Let's call it m. I know it will be bounded above by some number kasi si f triple prime ay continuous sa interval x minus h, x plus h. So ibig sabihin, ma-attain niya yung maximum o minimum dun sa interval na yon. Okay? Tapos h squared all over 6. Again, capital M is a bound for f triple prime of c. Okay? Plus, gagamit ako dito ng triangle inequality. So yung absolute value ni E1 minus E sub negative 1 ay less than or equal kay E1. Absolute value ni E1 plus absolute value ni E sub negative 1. Okay? Tapos nakadepende sa machine kung ano yung pinakamalaking truncation error, nakadepende sa number of significant digits na ginagamit ng computing software nyo. So basically, this guy will be bounded by some values of the machine precision. Let's call the machine precision epsilon. So this would be bounded above by epsilon plus epsilon. So this would be equal to 2 epsilon. Okay? So si epsilon siya yung maximum truncation error ng computer. And nakadepende siya dun sa computing device na ginagamit nyo. Okay? So essentially, we know that the absolute value of E1 minus E sub negative 1 will be bounded by 2 epsilon. Tapos, kokopyahin ko yung denominator na 2h. And luckily, this would be easy. Pwede kong cancelin yung mga 2's dyan. Okay? Now, this is our theoretical, this is our bound for the total error. So, para ma-minimize itong total error na to, kailangan kong kunin yung derivative niya. Okay? Okay? Tapos remember sa Math 36, alam na natin kung paano mag-minimize. Kunin nyo yung derivative, equate nyo kay 0, yun yung critical number, tapos sila yung posibleng magbibigay ng relative maximum or relative minimum. In our case, I take the absolute, I'll take the derivative with respect to h of e. So saan siya magiging equal? Magiging equal lang siya sa h m all over 3 minus epsilon over h squared. Okay? So yan yung derivative nung ayan yung absolute value ng derivative ni e with respect to h. Para makuha yung critical numbers, yung posible magbigay ng relative minimum or relative maximum, but in our case, it will be the relative minimum. Okay? Equate natin to kay 0 and then solve for h. Okay? So here I'll get hm over 3 equals epsilon over h squared. Multiply both sides by 3h squared, we'll get h cubed m equals 3 epsilon. And then so h cubed is 3 epsilon over m. So that gives us value of h is cube root of 3 epsilon over m. Okay? So ito yung optimal, ito yung approximation natin sa optimal step size para sa 3-point centered formula of order 2. Okay? And if we will apply this to the specific example I discussed earlier, remember ang f of x natin doon ay e to the x. So yung f triple prime of x ay e to the x din. Right? So ang maximum nito ay supposedly, kasi si e to the x ay increasing, so ang maximum value ni f triple prime of x as x goes from x minus h to x plus h ay equal kay e to the x plus h. Kasi increasing si e to the x, so ang pinakamalaki niyang value ay lagi nangyayari dun sa pinakamalaking x dun sa interval, right? So ang pinakamalaking x dun sa interval ay x plus h. So ang maximum value niya ay x plus h. Kaya lang gusto kong makapag-replace or makakuha ng replacement para kay capital M, which is simply a bound for the maximum value of f triple prime or an approximate to the maximum value of f triple prime. Ang idea nga lang dito ay dahil nakadepende siya kay h at ayokong gawing komplikado yung derivation, okay? I will use this crude approximation. Ano yung crude approximation? Si h alam natin should be a small number, right? Small enough siya para ma-drive down yung theoretical error. So kung si h ay maliit, all right? So kung si h ay maliit, so si x plus h ay malapit kay x. So ibig sabihin, the value of the maximum is approximately equal to e to the x for small h's. Okay? Kasi continuous si e to the x. So kapag ka yung x ay malapit kay x plus h, yung mga function values nila ay malapit din dapat sa isa't isa. Oh, by the way, here we are approximating f prime at 0. So yung x natin dito ay 0. So palitan ko na lang. Medyo nakakalito pala yung mga x's dito. So when x is 0, this would be minus h to positive h. So yung maximum niya mangyayari sa e to the h. Pero dahil si h ay maliit na number, so yung maximum na e to the h ay malapit kay e to the 0. Okay? Which is equal to 1. So I will use 1 as my estimate for m. Okay? So si m dito sa formula na to, pwede kong gawing 1. And then si epsilon, nakadepende dun sa computer nyo or dun sa computing software na gagamitin nyo. For example, dun sa yung table 7.1 na nabuo ko siya gamit si Excel. Tapos, chinek ko sa website ni Microsoft, si Excel pala nagkikip lamang by default ng 15 significant digits. Dahil 15 significant digits lang yung nire-retain niya. So at every iteration, yung normalized version ng floating point yung floating point representation nung number ay laging natatrancate lang hanggang 15 decimal digits. So the machine epsilon would be 10 to the minus 15. Okay? Kasi 15 decimal digits lang yung nako-consider niya. Okay? So I can replace the epsilon here by 10 to the minus 15. So 3 times 10 to the minus 15 divided by 1, then we take the cube root of that, we'll get an approximate for the optimal step size, which is this guy. So ito daw, or around this value, yung pinakamagandang step size na gamitin. It is small enough to drive the theoretical error down, but not too big so as to allow a large propagated error or truncation error. Actually, ang mas tamang term pala ay round-off error. Okay? So I hope the derivation is clear because you need to do this in some parts of the exercise. So any questions before I shift to Excel? Nandyan pa ba kayo, guys? I might borrow 5 more minutes. Siguro kailangan ng mga 10 minutes para ma-discuss yung Excel. Pero I hope this is clear. Andyan pa ba kayo? I hope you guys are still there, tahimik lang, or nagkakape, busy sa pag-aalmusal. So let me share my Excel and let's see how this is implemented. Okay. Okay. So I hope you can see my Excel. Tapos sana okay yung font. Okay. So try natin i-recreate yung table 7.1. So unang step size na ginamit ko ay 10 to the negative 1. So that's 0.1. Tapos ang approximate natin kay f prime ay e to the x plus h. What happened? Okay. E to the x plus h, no? Tapos ang x natin ay 0. So e to the 0 plus h minus e to the 0 minus h, kasi centered formula nga siya. And then the difference divided by 2 times h. So sa numerical diff, posibleng Excel na lang yung gamitin nyo kung ayaw nyo mag-MATLAB or Python. And I always think Excel is the best tool for these problems. So ito yung approximate natin para kay f prime of 0. And if we compute the error, kunin nyo lang yung absolute value nung approximate minus the actual value. We know the actual value is 1. So this is what we get. All right. And then what will happen if I decrease the step size by a factor of 10? So 0.1, i-divide ko by 10, yung previous h value. Okay? So magiging 0.01 na siya. Tapos I'll just drag the formula down. Okay? So nakita nyo yung pag-plummet ng error from 10 to the minus 3 to 10 to the minus 5. Ito yung na-observe na natin kanina dun sa table. And then let's try to do this and let's drag this out hanggang makarating tayo sa 10 to the minus 16. Kasi ito, nakita na natin, 44.5% na yung error. Okay? Or the error, the absolute error is 0.44489. And you will see the sudden spike in the theoretical, in the error incurred, in the absolute error incurred. So mula sa maliliit na value, bigla na siyang lumaki right after we hit 10 to the minus 14. So, and then let's see. Ano yung mangyayari if I drag this even further? If I drag that even further, kung makikita nyo, pagka 10 to the minus 17 na yung error, naging 0 na yung approximate. Bakit kaya naging 0 na yung approximate? Which doesn't make any sense, right? Kasi ang ina-approximate natin ay 1, pero bakit yung f prime of 0 ay approximately equal daw kay 0 kapag ka 10 to the minus 17 na yung step size? Any idea possibly why did that happen? Bakit kaya ganyan yung nangyari? Bakit siya nag-0? Okay, perhaps I'll go back to that later. Pagbalik ko dun sa notability. Pero let's hold that thought. Pwede nyo rin pag-isipan. Now, I'll implement this first using the optimal or the...
I didn't get that. The internet isn't reachable.
Okay, sorry for that. Nakikialam si Alexa. Pero yeah, so here, I'll implement it using the near optimal step size that we computed. So sabi dun sa computation natin kanina, the best step size is near 0.0001442249570. Okay? Siya yung gawin kong step size. And you see here that the error is 3.8 times 10 to the negative 11, which is, I think, the second best among what we got here. Natalo nga lang siya nitong, actually, third best pa pala siya. Natalo siya nitong 0.0001. So the thing here is that, that's why I emphasize na yung optimal step size nating nakuha ay approximation lamang, because we did some crude approximations along the way. Remember the value of m, in-approximate lang natin yung value ni m, tapos yung machine epsilon ay baka hindi yun yung eksaktong machine epsilon. That's just also a crude estimation. So, pero we know around what neighborhood natin makikita yung optimal step size. And you see that this is the optimal step size that we computed is between 10 to the minus 5 and 10 to the minus 6. And that's basically where we can find the best relative error, the best absolute error. Tapos if you want to shop for a better error, so makikita nyo na around this neighborhood ako dapat maghanap. So basically, probably I can divide this by 10. Oops, divide natin by 10. And we'll see, pag dinivide ko by 10 yung h na nakuha natin kanina, mas gaganda yung approximation. Actually, I think this is the best that I got so far, 4.2 times 10 to the negative 12. Okay? But I hope this illustrates the process, the improvement of the numerical differentiation formula by choosing the step size wisely. Okay? Now, I'll go back to the module and explain a little bit bakit una, nag-zero yung approximate pagka 10 to the negative 17 or smaller na yung step size. And second ay, bakit nga ba, or ulitin ko lang kung bakit hindi natin nakuha yung best approximate, yung best step size. Nakuha lang natin ay isang approximate dun sa best step size, but not exactly the best step size. Okay? Now, unang tanong, bakit nag-zero siya sa 10 to the negative 17 na step size? Well, remember, Excel has how much? It has 50, it keeps 15 significant digits. So kapag yung step size natin ay pag yung step size natin ay may magnitude na 10 to the negative 17, ibig sabihin yung unang non-zero digit ay nandun sa panglabing-pitong decimal, panglabing-pitong number after the decimal digit. Pero ang gagawin ni Excel, puputulin niya yun hanggang sa panglabing-lima. Okay? So ibig sabihin, wala nang natitira doon sa value ni h na idinadagdag. So essentially, h is treated to be 0 or near 0. So kasi sobrang liit niya na compared to the machine epsilon. So that means h here could be near zero or actually zero. So maging f of x minus f of x na lang yung ine-evaluate ni computer. Or kung kinip man ni Excel, yung 17 significant digits kay h. Pero once Excel computed f of x plus h, ikikip niya lang yung unang 15 decimal digits. Pag kinompute niya yung f of x minus h, ikikip niya lang yung unang 15 decimal digits. Kaya lang napakalapit ni x plus h at saka ni x minus h. So the difference between these two guys might be less than 10 to the minus 15. So posibleng yung difference nila ay order 10 to the minus 16. Kaya lang 15 significant digits lang yung tinitira ni Excel sa bawat iteration. So ibig sabihin, posible na along that calculation, naging number minus the same number yung interpretation ni Excel. So the numerator was computed to be equal to 0. Okay? And that's why when the step size is smaller than 10 to the minus 16, puro 0 na yung makikita nating estimate. Okay? Now, the second hanging question is, sir, bakit hindi sabi natin optimal step size yung hinahanap natin, pero hindi natin nahanap yung actual step size or actual best step size? Well, there are several factors to consider there. Okay? Una, ito. Ang inoptimize natin ay yung error bound. Okay? So, kasi hindi natin alam eksakto ano yung value nitong error term na ito. Because for one, we don't know the value of c to plug into the third derivative. Pinaltan lamang natin siya ng isang constant m, which could be convenient for us. And then also, actually, pwede ko tong gawing eksakto or gawin kong mas maganda yung error bound. I can replace it by e to the h. Kasi sinabi natin within the neighborhood of 0, the maximum of e to the x would be at e to the h, right? So pwede ko tong gawin. Kaya lang, remember, i-differentiate natin to. Pag differentiate ko to, magpa-power rule ako involving exponential. And I need to equate the derivative to 0. So that will end up with a nonlinear equation, right? Or a transcendental equation na mahirap isolve manually. Tapos yung numerical techniques para isolve itong nonlinear equation na to ay nasa math 175 pa. So that's why I was restricted to just replace it by a constant approximate. Okay? Kaya yon, posibleng cause siya, kaya hindi yung eksaktong optimal h yung na-compute natin. Pangalawa is the machine epsilon. Remember, it should not be the machine epsilon. It should be the absolute value of the truncation in the first number and the truncation on the second number. Pero hindi ko alam yung eksaktong value na yon. Nakadepende yon sa iba't ibang factors. Number one, computations inside the machine. Saka nakadepende rin siya sa numeration base ng computing device. Kung binary ba yung computing device or siya by hexadecimal or decimal siya. Kasi ang ginagawa ni Excel, pag nag-input ka ng number, i-convert niya yon sa kanyang floating point representation. Yung floating point representation niya, nakadepende kung ano yung base ng numeration system. Some machines or some computers do calculations using binary digits. Yung iba decimal, yung iba base 16 yung ginagamit. So it's not as simple as putting the machine epsilon to be 10 to the minus 16. Marami pang factors involved yon. But for simplicity, we just assume it is an epsilon, which depends on the number of significant digits. So yun yung ilan sa mga dahilan or posibleng dahilan bakit hindi yung eksaktong optimal h yung nakita natin. Kasi nga, yung differentiate natin is a crude approximation of the total error. But yeah, but nevertheless, we got a good approximate for the best step size. Yung nakuha nating step size na to ay hindi ganun kalaki, hindi rin siya ganun kaliit. It's right, there's a good balance between the theoretical and the round-off error. Okay? Unfortunately, I wouldn't have the time to discuss example 7.1. So you can do this as a practice para sa lab excerpt. So nandito naman yung detalyadong solution. Medyo may mga typos nga lang dito. Let's see. So yung number 1, review lang siya nung module 6. And then the theoretical error is big O of h cubed. All right. Tapos, ano ba yung mga kailangan kong sabihin dito? Well, here. So ito yung error due to truncation. Bakit siya naging 40E? Actually, ito dapat ay 40 epsilon. 40 epsilon nga ba siya dapat? Yeah, I think that's 40 epsilon. Sorry, sinabi ko pala rito ay E, pero dapat epsilon din yan to be consistent with the notations. Bakit siya naging 40? Kasi gagamit ako dito ng triangle inequality para dun sa absolute value niya. So that would be less than or equal to 2 epsilon over 6h plus 9 epsilon all over 6h plus 18 epsilon over 6h plus 11 epsilon over h, right? So nasa loob siya ng absolute value, tapos bibigyan ko sila bawat isa ng absolute value. So what we'll get would be positive this, positive of this, positive of this, plus that positive, divided by 6h. So the total would be 40 epsilon all over 6h. Tapos mali yata dito yung fourth derivative ko. Let's see. Yung function ay sine. So sine, first derivative ay cosine, then sine, then cosine, then sine. So dapat pala to ay sine. Positive or negative sign, it doesn't matter kasi nasa loob naman siya ng absolute value. Tapos ito na naman yung crude approximation. I want to get the maximum of sine over the interval x minus 3h until x kasi backward yung formula. Kaya lang, I don't know exactly what or how this interval looks like, but I know that sine is always bounded by 1. Okay, or the absolute value of sine is always bounded above by 1. So nangyari, ni-replace ko siya by 1 in this particular example so that this guy would be my estimate for the total error bound. And using the same technique we did earlier, it was found that the optimal step size is near 0.091798. Okay, so I hope that's fine. Kindly take a look at example 7.1, reading assignment na lang siya. And that would be and that would be all for today. Next meeting we'll start with another improvement for the numerical differentiation formula. Ang concern naman niya ay convergence. Yung ginawa natin kanina, ang concern niya ay accuracy with respect to machine implementation. Then next time we will be looking at how to speed up the convergence of the numerical differentiation formulas with respect to H. Okay? Now, before we end, any questions? Paramdam naman kayo guys, parang isang buong oras ako nag-monologue dito. So, yeah. Sana next time parang podcast naman na meron akong kausap or my guest para hindi lang ako yung dada ng dada. Okay? Any questions, guys? Okay, if not, then thank you very much for joining me today. I really appreciate the effort na gumising ng maaga, even though the recording will be up in a few minutes. Thank you for keeping me company this morning. I hope you enjoy the rest of the day, and then let's see each other again on Friday. Bye, everyone.